coming back just a bit, the experiment with bivalves is a bit complicated by the fact that bivalves, for example, they are suspension feeders and then feed on particles, and then to carry out experiments with food we need to use particles, and then we need to count particles. This is possible just through different methods. Probably the most common, probably the most precise method is just the Coulter counter methods. And then our setup is quite simple because we feed organisms with different amount of food, and then we measure the ingestion rate. We can do it at a different condition of temperature, different conditions of other stressors, and then we do usually also on gastropods in this moment in my lab, and on Erythia verrucosa, which is a crab. Clearly the method changed totally, because if in mussels we need to feed with phytoplankton or particles our animals, in this case we can use praise, just bivalves as a praise for Erythia verrucosa, with a lot of different setups, just to pay attention to the different condition, experimental condition, but the experiment is quite simple. This is the DEB model in which, but don't scare, because before we had just a fish, tuna. This is a formalization of the DEB model. But what I want to show is that what is the meaning of mechanistic? Mechanistic is a very simple concept. This is, in the end, a car, an engine. These are parts of this car. And then when we design a car, we have pistons, cylinders. We have just different components, just designed just to reach the optimization. And then what means mechanistic? It means that if we know how these species acquire energy, how works at different kinds of energy, and then how process energy, we can also, using all different components of the DEB model, we can estimate also the number of eggs produced per lifespan or per reproductive events. The same if we can, if we, for example, if we have a stressor altering the somatic maintenance cost, like a contaminant, the cadmium, for example, and then somatic maintenance cost increase, in theory, we can, in practice, we can use just these to get information of the amount of eggs produced per lifespan or per reproductive events. Pay attention also to another concept. In this case, we measure the Darwinian fitness, which is just the number of eggs produced which an organism is able to produce per lifespan. Is not the fitness, the ecological fitness, which is instead the number of kids, I don't know, that will reproduce, and then in birds, the clutch size is the Darwinian fitness, the number of small birds coming again in the same place in the next year, which are able to reproduce. This is the fitness of every organism, of just two animals. In this case, we just have the Darwinian fitness, the number of eggs produced under different conditions. This is important because it's totally different totally different to think to one organism producing 1,000 eggs a year, or the same organism is able, under different conditions, 10 millions of eggs a year. These are two different numbers affecting totally all the components of the population dynamics, because the dispersal, for example, of eggs in our marine animals usually is a process in the end which is density dependent, and then all population the most component of the population dynamic are density dependent, and then we need to understand how many eggs one organism is able to produce under specific conditions. And this is the core of the message. Just the DEB, just to repeat, to repropose this information, this is just the DEB, and then we capture the stochasticity, the environmental stochasticity. We translate this in effects on functional traits. Since we can't measure the eggs and the gonads from all organisms in a population, we need to use models, and then we can use a mechanistic core in this framework to estimate the number, the magnitude of life history traits. If I can do it, I am able to do it, I can use this amount of eggs just to feed the dispersal and then all components of all ecological components, which are based more or less on density dependent processes. And then if I produce here 1 egg or 100 millions of eggs is totally different. Probably these affect the population dynamics in a way totally different. And then this is the main output. The idea is to feed with eggs a population dynamics module, an age-structured discrete population model with monthly step. Is pretty complicated, but we can use the fecundity, the Darwinian fitness, based on this mechanistic core, just to infer now on the population dynamics. Population dynamics which have 4 components: emigration, immigration, birth, and death. And then we have an important driver, which is birth. Immigration, emigration, and death are matter of just experiments in the field, because if we want to understand how many eggs reach the adult phase, we need to measure it in the field. But in this case, we can use the fecundity just to run our model.